Well, it's really fun to be speaking here again at LMR community. And I wanted to thank Julian for putting this together, and happy to share today with you and share some of our latest lab results from the coral domain. And my title kind of echoes a reviewer comment that I got several years ago, maybe 5 or 7 years ago now. And the reviewer comment said, one has to wonder when, you have too much data from a single place. And I've been wondering about that for a very long time, and I still can't answer that question. And Greg just provided me another impetus for just getting more today. So I'm going to show you what we're about, and I have to acknowledge help from a vast army of people in my lab over many years, including Alyssa, who's here, and Sam Stevenson, who's been a very important collaborator over the years, as well as Chris, Charles, and Larry, and Hai, who have been really instrumental in initiating the project ages ago and are still great cheerleaders. And great funding continually from NOAA, well, not now, but in the past, and continually from NSF, so it's been great. So these are just some of the questions that we noodle on in this community, with relationship between modes like El Nino and forcing, and we look at volcanic and natural forcing as well as greenhouse forcing. We also like to think about mean state and the character of these modes and forcing and this whole bunch, and we can have a lot of different playgrounds for that. This particular playground is last 1,000 to 2,000 years. And then I put this third one here, which is stolen a little bit from my PMIP talk, although substituting the question about ENSO properties to blank properties, because as we heard from the multi-decadal drought community, it's kind of throwing their arms up like, what does all this mean anyway? So really, this is extremely timely to kind of keep gnawing on these questions, and they're important for future climate. And so this is my lovely picture, for those of you who haven't seen it, of me dressed significantly differently, the different breathing apparatus, drilling fossil corals, in this case a modern coral, obviously, in the Central Pacific. We've been working there for a very long time, and we have also achieved a huge archive of fossil corals that have been washed up on the beach by wave activity or storms or tsunamis or something over many, many millennia, as I'll show you. And we've been collecting those what feels like over millennia, but is really only 20 years. So here's what we do via scuba. Pushes us back roughly 100 years. Many of the records that exist in the Coral Archive are really exist in this domain, drilled from this kind of environment. And then this is the playground for what I hope to be a new generation of folks to go out and gnaw on and push these archives. I just got an email from Thomas Felis noting that he was down in the Marquesas and he drilled 24 meters of core from the Marquesas in the last week. And so he's very excited. So he's really on about this and really expanding these records back in time. In this case, we have from the Line Islands in the Central Pacific, 7,000 years of potential material. Okay. And so coral delta 18, we've already heard a lot about it. So this is just a picture of one to bring it into focus, the archive and what it's like. So it accretes about 1 to 2 centimeters per year, which affords monthly resolution of this proxy that we apply, measured by mass spec, and that is a function of sea surface temperature and the delta 18 of seawater. And this generally co-varies with sea surface salinity, and people have alluded to that over various talks today. For the most part, it's not perfect. That relationship changes through time, and we know that from looking at a first kind of seminal papers and going back to Fairbanks, 97, and then going up into Schmidt when he expanded a global database, further elaborated upon by Legra and Gavin, entering into the model domain, and then Jess Conroy through work in my lab showing just how variable that relationship can be through space and time. So for those of you who really want to get obsessed, you can check out those references, and this is an ongoing area for much needed constraints that simply don't exist on this relationship. But we say that we get lucky in the Central Pacific because when it gets warm, it gets wet. When it gets wet, salinity goes down, and oxygen isotopes of seawater are likewise driven down. And so this is a great place to use oxygen isotopes with all of its foibles because we are compounding signal-to-noise ratios for the signals of interest. So this is for the El Nino of 2015, 2016. When you get warm, you get wet. But obviously on longer timescales that are relevant to LMR, the relationship between warm and wet kind of may fall apart or change in character. and that we do all of our calibrations on interannual variance, and we have very little information about the lower frequency component of the sea surface temperature and delta 18 seawater contributions. A huge caveat for LMR in all those beautiful coral records that you're using. So this is a calibration plot showing us the different kinds of modern coral records that my lab has generated. We have a lot more data than this. I'm just showing you a kind of a cleaner plot. I think I have a Mister one in a second. But here we have OISST in gray and the different colors of monthly delta 18 from Christmas Island, and plotted as all the red, blue, et cetera. And they obviously look very, very good with sea surface temperature, and if you have more records, you feel much better that you're reconstructing the amplitude and frequency of ocean temperature extremes related to El Nino and La Nina. Of course, this is a beautiful time interval for us to work in and have a proof of concept. When you start going back, the data start decimating even in this interval to the 20th century. Earlier in the 20th century, we have like 1 or maybe 0 records from the Line Islands. So it's really a challenge going back in time beyond this interval. But this is good. This gives us an idea that we can do pretty well if we throw a lot of records at it. Here's work by my undergrad, Gemma O'Connor, piling up a huge number of records that we drilled in 2016 at the end of the El Nino event. So we drilled really, really short cores, many, many, many of them. And this is where you get a little bit brash because you spend so many years as a coral researcher trying to poke as few holes as possible to preserve the reef, right? And then it gets wiped out by a big El Nino event, and you worry that you didn't drill enough over all those decades. So I'm done with that. I am just drilling a lot of holes in these reefs now. When I find a coral that survived the El Nino event, I'm like drilling that, like 1 in 5% coral there. Okay, so here's what she did for her undergraduate thesis in my lab. She piled up 12 different records across the 2015-2016 El Nino event. And this is really where I hope the field is going in the coral world, where we can actually generate ensembles of coral delta 18 records through time and not just one record, right? This is really critical. We can kind of do the tree ring thing, but hopefully we can really have a wonderful calibration interval that feeds seamlessly into a stack of ensemble records going back in time. And this is my aspirational model that I think Gemma has really brought to bear over the last El Nino, which is a particularly important mark, and I'll show you why. So the benefit of doing this over kind of real time, last decade, is that you can compare this with temperature records, of course, over the calibration interval, as well as delta 18 seawater, or you have it. And in this case, I'm showing you output from Sam Stevenson's ISO-ROMs, where she was able to do kind of a pseudo-coral comparison with the real coral. So the pseudo-coral is in blue, and the real coral is in black. It actually looks really, really good. And in ROMs, you can decompose the temperature and the delta 18 of seawater. And in this case, of course, she finds in that paper that this is the 2015, Stevenson et al. 2015, that SST is really the dominant driver for this comparison. So over 90% of the variability is coming from sea surface temperature. But obviously, is this accurate? We have really very few sea surface salinity. And then even if we did, translate that into delta 18 is really difficult. We don't have delta 18 of seawater. So this is why it gets really important to go out and measure these things. We actually have to have observations. I know that's like a crushingly difficult thought because these are not easy to get. And so I'm going to show you one example of an effort to do that. And over the last El Nino event, so we were funded by NSF to go out there and get real observations of this stuff. And it's very exciting. I spent a lot of time along the equator, as did Alyssa and Sam, my other students. So this is the composite from Gemma O'Connor, with, I think, how many? Six of the corals that we're plotting right here that span this interval. And then these are loggers that were deployed at the site over the El Nino event. We have kind of one errant logger up there, but the rest of them look like IGOS or Togatau. And this is salinity data from a CTD right here, which is showing you a decrease in salinity. This is the wet conditions I was talking about impacting the surface mixed layer. And then this is delta 18 of seawater here, which is also very kind of variable and very spotty, and my Picaro's down, so that's why I don't have more data for this plot. Anyway, hopefully we'll have more data. But if we just kind of attach some rough constraints on these observational data that we have anew, the change in coral delta 18 is maybe minus 0.7, 0.8. SST is maybe 3.5 to 4 degrees. Delta SSS is definitely full up 1 PSU. And then the delta 18 in seawater, poorly constrained, but 0.1 to 0.2 per mil. And so we can kind of add these up, and we can say that, in general, from this El Nino event, we'll have a lot more data for this, especially this plot right here. We'll have about 150 more data points soon, which will be super great. But for this event, we can say that 80 to 90% of the coral delta 18 anomaly was driven by sea surface temperature. However, this is just one El Nino event. It was a certain flavor of El Nino event. Maybe other El Nino events are different. Obviously, they all are going to be different, and we only have this event to calibrate on. So this is just to say that if you can kind of take this ensemble approach back in time, this is what the kinds of information you can get. So this is across 40-41 El Nino event, the 82-83, 97-98, and here's the one we really have the most core from. Can we get more cores from this interval in time? Yes, we can, because we have the fossil corals. I'm going to show you the huge promise that we have from that. So we can create you an ensemble of the 40-41 and all of these other events going forward, and this is what we're going to be doing going forward. Of course, all the corals at Christmas Island got completely wiped out. It was death, mass death at Christmas Island. 85% of our corals died during the last El Nino event. And so this archive is gone, like, period. You will never drill another modern coral record at Christmas Island that predates 2010, ever. It will never happen. It's gone. But thankfully, we have these beaches that are littered with thousands and thousands and probably millions, actually, of coral records that we can go and use. If we want it badly enough, we have this archive perfectly preserved on these beaches at Christmas Island. And we have been just trying to milk this for all it's worth. So we've conducted many expeditions. We collected thousands of corals. We've dated thousands of them, even with radiocarbon and U-series. And we have run a subset for sub-monthly delta 18. And we've run quite a few for bulk delta 18. And that's what I'm going to show you. That's what Alyssa's been focusing on as well. So this is an amazing archive that we can use to push different intervals back in time. So last century at Christmas, looks like this, and this is something that Nick Hitt is another undergraduate in my lab has been working on, where he's been looking at uranium-thorium dated sequences that fall in the last century and trying to see how well they reproduce sea surface temperature. And so what I'm plotting here is a pseudocoral based on ERSST, as well as the modern coral. Modern corals are in gray. You actually can't see that gray, but it's very much under the black. And then the blue are the fossil coral sequences that we picked up off the beach and uranium-thorium dated and plotting here for you. And the bottom line is that I haven't offset these blue corals at all. They're just literally falling where they are as translated through temperature through the calibration interval. And this would suggest that the corals are doing a brilliant job at reflecting temperature, or the temperature is doing a brilliant job of reflecting corals, or both, or none maybe. But the bottom line is that these data do fall on top of ERSST, and that this would imply that there's perhaps little room for delta 18 of seawater changes across the 20th century at this site. However, we have to keep in mind this asterisk. We need to get a lot more corals to this interval, like ensemble the heck out of this, and then we could say something more concrete about potential trends in seawater delta 18. But it's this very exciting avenue, and this is really kind of proof of concept that Nick was able to do in kind of green lighting us to just push forward full bore if we wanted to. The last millennium kind of looks like this. This is work by Tianran Chen, who was working in my lab a couple years ago. We're trying to get this published. We may never, but anyway, maybe Alyssa will just publish it for us. So this is uranium-thorium dated sequences from Christmas Island, run at monthly resolution. And so we're coming up into the present here. Here's the 2015-2016 El Nino event, achieving a record delta 18 coral value for the millennium, as much as we have data. Perhaps not a surprise that it reflects the hockey stick in some extent. But there's a appreciable amount of kind of scatter in here. These are the mean values and the monthly spreads around them. And so this guy's way low right here, and we're right next to this guy. So again, we need a lot more data to kind of ensemble through this millennium. But this represents a challenge for LMR. How do you treat such an ensemble of data in a data assimilation context? It's pretty to leave this on the table because it's a very important constraint. But on the other hand, there are going to be error bars in the dating direction, as well as some kind of reflection of an error bar wrapping through this as well. If you look at the last 6,000 years at Christmas Island, this is Alyssa's work. This is what it looks like. So this is combining now going back to 6,000 years ago, just at Christmas Island, We have the modern corals in kind of red circles, and we're just reflecting the mean. For this plot, we're really just interested in the evolution of the mean. And then we have the high-res data in blue, in part borrowed from Pam Groth's dissertation that she just finished at Georgia Tech. And then this new approach that Alyssa's really been leveraging is just applying a huge amount of bulk measurements to the uranium thorium-dated corals that we have from Christmas. And so again, if you want to, you can spend a whole month generating 100 years, well, actually take you several months, 100 years of delta-18 data from sub-monthly resolution. Or you could just mill that whole axis and say this is about 100 years and homogenize it all up and get 4 points in a couple hours. So that's what Alyssa's been trying to do, to try to beat back the error of the archive as well as the variability that's coming through this whole interval. And again, the idea would be to create an ensemble of coral delta-18 estimates that could guide the kind of work that is going on here. However, again, new challenges with how do you use this kind of information in a simulation framework. So, going to the last 7,000 years now and bringing you up to speed with the latest El Nino results from our lab. Pam Groth's dissertation just wrapped up. She's now at Mary Washington in a new faculty position. And so this is the sum total of all the coral data we've been running at sub-monthly resolution for El Nino variants, going back 7,000 years, and now taking all the islands into account. So we have Christmas, Fanning, and Palmyra here. They're all uranium thorium dated, and they contain anywhere from 8 of the open circles all the way up to 315 years in the case of this beautiful sequence, which it falls in the Common Era. And so what we can see here is that with respect to the benchmark, which is kind of arbitrarily chosen, is late 20th century El Nino variants. So stronger than that is stronger than the late 20th century, and then below that is weaker than the late 20th century. You can see that most of the data are actually falling below this dotted line. And so this would indicate that we actually are in an era of relatively strong El Nino variants with respect to coral delta-18 in the Central Pacific. And so that's one observation we can make. And the second one I would make, just in case folks are interested, this is a major thrust of our paper, is recognizing that this is also an interval for significant reduction in this case for El Nino variants in coral delta-18 in the Central Pacific from about 3,000 to 5,000 years ago. A conclusion that Julian had knocked on in his 2016, 15, something, Nature Geo paper. Oh, okay, that's why I always get confused. So Julian had kind of mentioned that as an emergent signal. Now we're able to pin a lot more data on this with Pam's thesis, and we're able to test this against a variety of different nulls in assessing its significance. And here you'll see the LME coming in prominently as an important null for constraining the variance in El Nino changes that can happen by chance undersampling. And then the other null that we're choosing here is Antoinette Capatondi's linear inverse model trained on 50 years of El Nino variance in the instrumental record. And so basically, when these green bars are exceeding the significance thresholds for these nulls, we can imply that there's a significant change in El Nino variance with respect to this null in coral delta-18 in the Central Pacific. And so we have these two conclusions. There's been a decrease from 3 to 5, and there's been an increase from the pre-industrial as a whole into the last 50 years of record that we have available. And so there's some fine print that is kind of, obviously critically important, dependent on how much you buy these nulls and whether they're actually an accurate reflection of reality or not. So remains to be seen, but this is the best in the business that we can choose right now, and we think that they're appropriate. And so these are other references that are noting. I think it's an exciting time in El Nino research because we have some emergent signals from several different proxy reconstructions telling us that El Nino variance actually is increasing in the last several decades with respect to the pre-industrial era. I was involved with one such study here from Taiwan, a very impressive replicated annual resolved record of 14 different, this is crazy how much data they ran. I mean, I've never seen so much data in one paper. So there's 14 replicated annual reconstructions of tree cellulose delta-18 going back to 700 years ago. So it's 1200 AD or so. So a great resource for LMR and something that was, again, showing a change in variance coming into the 20th century. So I wanted to switch gears a little bit from what we found in Coral World to what this means and what we can do to really utilize these data the best. And of course, this is going to bring me right back to my favorite thing, water isotopes, and how little we know about them and how important they are in corals. And so we kind of have to keep in mind that we're dealing with this moving soup, right? Here reflected in sea surface salinity. This could very well be delta 18. So climate, can push on this soup, which can advect different delta 18 seawaters around. We also have water coming into this soup and mixing around, and that can change delta 18 of seawater. And of course, the rainfall is changing with respect to climate as well. So we have basically this dynamical soup that's very poorly constrained, especially in the tropical Pacific. And so I wanted to say that this is a project that we just got underway. Pages just green-lighted this. So myself, Neroli Abram, Thomas Felis are doing a new coordinated effort through Pages called Coral Hydro 2K. And it's an effort to bring new coral delta 18 records in combination with coral strontium calcium records to bear on the problem. We're going to have a heavy focus on the last century because that's where we feel we have the most capabilities of milking an archive for new records. But we're also interested in working with modeling folks who can help us tease apart the relationship between climate and salinity and delta 18, as well as how to translate those into archives through proxy system models. So this is, I hope, going to take us the next step with respect to corals specifically. And I just wanted to also give a plug for my student Hussein Sayani's work working with strontium calcium. And I believe that that is not going to be the answer to this problem. It's not going to deliver us a fully constrained set of solutions where we're going to say, oh, just put it in the bank and we'd be so happy with ourselves that now we can independently assess delta 18 of seawater from a single coral record measuring two different geochemistries. That's not probably going to happen. But however, we can do a lot better with how we are really relying on getting better records from these corals. And so again, through ensembling, I hope you're kind of getting that picture now. This is what we need to be doing. It's a lot of work, but he's running here 5 different coral records at monthly resolution for coral strontium calcium. This is at Palmyra, where our signal is very, very small. And here he's showing you the individual records, and here's the stack with respect to sea surface temperature. Any one of these records would not look as good as this composite strontium calcium record, but together they look pretty amazing. And so again, if we wanted to go back to the early 20th century and go crazy with the ensembling approach and run delta 18 and strontium calcium, we're going to uncover some new information. But it's going to take a lot of work. Wow, that's like staggering amount of 5-year plan there, but still, if we wanted it, we could get it. And so where we're going with the OBS is trying to lift up the observations that are underpin our dynamical interpretations. I'm running this crazy network I talked about last year at LMR. This is really work that Jess Conroy started in her postdoc with me, also in collaboration with David Noon through an NSF proposal that we had, and Jessica Moorman, whose work was already featured here. And so we're having seawater and rainwater collections across the tropical Pacific because we simply don't have the data to figure out how well the models are doing. And so there seems like a critical mass emerging, and I had many conversations at PMIP last week about this. I gave a huge plug. I'm going to Clivar. The Pacific panel is meeting in 2 weeks in Korea. I'm going to take this there and throw it in front of them. I have a whole day to make my case with these people, and I think I'm going to get somewhere. And so we need a new observational network designed and kind of with new scientific motivations that bring this space to light with respect to its implications for modern climate dynamics, as well as, of course, our own favorite past climate implications. And then we also need to think about archive structures and capacities, because I, for one, have a huge amount of data that's coming out of my lab, and I don't really have anywhere to put it right now, which is kind of depressing and very limiting for our community. So if you're interested in that, let me know. There are some very near-term opportunities, like the next 10 days, to get involved in the ground level at some kind of dear colleague letters that David Noon and I are thinking about. And this is something that I just learned about at PMIP, which is a new working group through Pages called DAPS. It's paleoclimatology analysis, data assimilation, and proxy system modeling. And so Diane Thompson was talking about this at the PMIP meeting, but Hugh Goose and Mike Evans are kind of the big leaders there for this effort. And they just met in, I think it was May, and one of their main near-term goals is a 20th century reanalysis piece. And so we've heard again and again today how your approach, your data, your concerns are going to be target dependent. And so I think this is a lovely place for us to throw some effort behind making that effort successful and learning what we can from that effort. And so I, for one, am going to be very closely watching that. I really encourage you to kind of raise your hand and say, how can we make this proving ground of new methods and data work? And this is, I think, very exciting. This is what the modern climate people really want to see us do, is a 20th century reanalysis that they can use to ask really key questions about changes in hydrology, changes in ocean circulation, changes in extremes. Okay, so just to summarize, I don't really have the data-driven summaries other than to say that I do believe that the coral ensembling approach is the way forward, where we can actually beat down some of these errors while delivering quantifiable uncertainties to folks like yourselves. We've seen how this can beat back errors in proxy kind of uncertainties, like strontium calcium. So it's kind of like make coral strontium calcium great again. This is a hard path where we can actually pave the way for really robust reconstructions that we haven't been able to crack before. Strontium calcium has been like, the poor stepchild for about a decade. And some people say it's terrible, some people say it's great. I say it's great if you really work hard to replicate those records. That's where it's great. And there's new opportunities for this coordinated research in water isotopes. Maybe that's something that could emerge from LMR as a new kind of, wow, we really need to understand this better, and how do we do this in the context of LMR. And then also just to kind of play for what's coming next for us, I'm going to ensemble the heck out of the Tambora eruption, which I'm really excited about. We've identified 20 plus corals that may span that time interval, so we're going to be throwing a lot of data at that. I'm very excited. This has implications for mean climate since then, as well as, of course, the response to volcanic forcing. And then whatever kind of nested within a broader project, which is going to target 18th, 19th century, well, actually 19th to 20th century ensembles for both Delta 18 as a first pass, and then where we really want it, ensembling coral strontium calcium as well, something that Alyssa is going to be working on in my lab for the last 6,000 years as well. So yeah, I'll end it there. Thank you.